When we compute the average rate of change of a function, we're looking to spread the net change of the function out evenly over a certain interval. In this example, my x-axis is the hours that we spent driving, and the y-axis is the miles that we've covered during that time. So the first point of data that we have is that after 1 hour of driving, we've covered a total of 40 miles. And then the second point of data is that after 3 hours of driving, we've covered a total of 70 miles. If you look at the graph between hour 1 and hour 3, you can tell that for some portion of that, we're not driving at all. These horizontal places where time is increasing, but the mileage is not increasing. And then for some portion of time in the very middle, we are traveling a certain speed. But the fact that we've spent time not driving has lowered our average speed overall. So how can we compute the average speed during this time? Well, first we want to ask, during the time, how much mileage have we covered? And the distance we've traveled here is we ended at 70 miles and we began at 40 miles, and so that's a net change of 30 miles. And the second question would be to ask, well, how long did it take us to do this? And we ended at hour 3 and we began at hour 1. So it took a total of 2 hours to accomplish those 30 miles. And then to average those, we need to take the 30 miles we covered, that's the change in our function, and divide that evenly over the 2 hours that it took us to accomplish this. And that gives me 30 miles divided by 2 hours is 15 miles per hour. That's our average speed for this time. Another way of thinking about the average speed being 15 miles per hour is that if we had started driving at a speed of 15 miles per hour at hour 1, and kept that speed constant throughout the 2 hours until we get to hour 3, we would have covered exactly the same distance as we did by not driving for some amount of time, and then driving quickly, and then not driving again, which is what the graph shows. So we computed average speed by saying this is the net change in miles divided by the change in time. And this is true for functions in general, that the average rate of change of a function is the net change in y, or the net change in f of x, the output of the function. And we want to spread that evenly over the change in x that we're looking at, so we divide by the change in x. So here's another example. On my x-axis, I have I'm measuring years, and on my y-axis, I'm measuring the population of some town in thousands. The second year of measurement, the population of town is 5,000. We'll just denote that by 5. And at the 20th year of measurement, the population of the town is 50,000. So what would be the average rate of change of population over the years 2 to 20? That is, even though we can tell from the graph that sometimes the population is changing quickly and sometimes the population is changing slowly, what would be the average rate of change? That rate of change that if it held constant would get us smoothly from 5,000 to 50,000 over that time. Just like before, we need to compute the net change in population. That's our y in this example. And the net change in population is the 50,000 we ended with divided by the 5,000 we started with, and so that's a net change of 45,000 people. And it took us 18 years to accomplish that because we ended at year 20 and we began observing at year 2. And so 20 minus 2 is giving us the 18 years that it took. And that means an average rate of change of 45,000 people divided by 18 years, which comes out to 2.5 thousand people per year, or 2,500 people per year. I represent the 2.5 thousand people per year as the slope of the line connecting the 2 points of data that we have, rather than the graph we're given, which shows that sometimes the population is increasing fast and sometimes it's increasing slow. When we compute the average, it becomes this straight line segment that increases at a constant rate from the point of data 2.5 to the point of data 2050. What about one where we don't have a graph, but we simply have the function? What will be the average rate of change of the function 1 minus x squared between x equals 2 and x equals 5? We still have to compute the net change in y, and to do that we need to say, well, what is the ending value, that's f of 5, and subtract the beginning value, which is f of 2. We plug these into the function and simplify to get minus 21 as our net change in y. Now what about our change in x? Well, we ended at x equals 5 and we began at x equals 2, and so that's a change of 3 in x. And then we can get our average rate of change. This is the net change in y divided by the change in x, just like it was for the graph. This gives an average rate of change of negative 21 divided by 3. Those are the two values we computed. And we get an average rate of change of negative 7. And what are the units for this rate of change? Well, since there's no context, all we can say is that we lose 7 units of y. The y value decreases by 7 every time we increase the x value